Hello, everyone. Today I'm standing outside of Chernobyl, the site of the worst nuclear meltdown ever in human history. That is actually, believe it or not, a tourist location today. And so I think it's only fitting because what I want to discuss in this lecture is the effects of radiation, um, the different types of radiation and what it does to um, the body, and then go into a little bit of how we measure radiation and quantify it and determine the absorbed dose that we are exposed to. So let's share the screen and get started. Okay. So I included a little link to like a short video. I think it's 2.5 minutes or so long about Chernobyl and the and what it looks like today. Interestingly, there was a Ferris wheel, and it was, according to this video, scheduled to open a few days after the meltdown. So it still stands there to this day and has never been used. And in this picture, it looks like there are people there. So again, Chernobyl is a highly radioactive location. Yet I guess there are places within Chernobyl that are relatively safe to come in contact with. In fact, as you can see, it's pretty overgrown now. The wildlife has started to reemerge in that area. Ecologists are studying it to see the effects of the nuclear reactive presence on the biology of these animals and how they're evolving. And so I just recommend you just check it out. It's a really quick video. And again, if you haven't seen Chernobyl, the show, the miniseries, I recommend it. So radiation comes in different forms, right? Different frequencies. And so it's going to have different effects on the human body. But uh, with that in mind, what we've done is that we've developed this universal system, okay, to account for all the different types of radiation and to assign a given amount of radiation to an overall effect in the body. And the way we measure that is in REMS, which I'll get into later on in the lecture. But this chart is just kind of breaking down the different exposure levels to the side effects. So anywhere from 5 to 10 REMS, which is actually kind of the cutoff, the maximum amount of exposure that we like to, that the government likes or chooses to um, say is acceptable. That level will start changing things in your blood, changing the hemoglobin and its ability to bind oxygen, maybe changing some of the immune cells in the blood as well. But certainly some chemical effects in your blood will be visible at this rate of exposure. You get anywhere from 5 to 10 times that amount. And then within a few hours, you'll start feeling nauseated. You'll start feeling tired. You bump it up to 70 REMS, and that can be associated with vomiting. 75 rems is going to be now hair loss. 90 rems, diarrhea. And then once you get up past 90 rems, you get into the bad zone. So at 100 rems, you're going to start hemorrhaging. And up to 400 rems exposure, that's going to be death. Okay, most likely. 1,000, if you are so, I guess I hate to say lucky to make it to that extent of exposure, because there's nothing lucky about that, of course. But if you were able to survive past 400, then you would start seeing destruction of your intestine and your your enteric system, internal bleeding now, and definitely death within a few weeks after that exposure. And again, I think this is not cumulative. This is probably if you were zapped with 1,000 rems at once. 2,000, damage to the central nervous system, loss of consciousness, and again, death. And that's going to happen within minutes. So if you get a lower dose, 400 rems, you can still die, but it would maybe take a couple months, right? Whereas you double that to 1,000, it's going to take a couple weeks. You double that again to 2,000, and now we're talking, anywhere from minutes to hours to days. So certainly the amount of exposure is proportional not only to the side effects, but to how quickly the onset of those side effects are going to occur. There are two main forms of radiation. One is non-ionizing radiation, and this is the lesser of the two evils. The non-ionizing radiation is going to speed up the movement of atoms and molecules. So think of microwaves, which is the equivalent of heating the sample, right? So when you put food in the microwave, the non-ionizing radiation is moving around the atoms, primarily of the water molecules in that food. And as you know, when things move, the more they move, the more heat is associated with that, right? Being in that system. It's going to take a lot of non-ionizing radiation to reach a dangerous threshold, okay? Conversely, with ionizing radiation, that is not going to take a whole lot of exposure. That is much, much more damaging to the body. It can break apart the bonds in our DNA and our RNA and our proteins and our other biomolecules. It can remove electrons and create free radicals, which then will attack other biological molecules, rendering those molecules functionless, right? And so these are the two main forms. And if we look at the spectrum here, as you can see, we have visible light here, and then we have the short wavelength ionizing radiation to the right, and the longer wavelength non-ionizing radiation to the left. And interestingly, UV radiation kind of flanks these two forms, okay? So UV radiation, which comes from the sun, can be non-ionizing or ionizing depending on what the frequency is. So if we're looking at this longer wave UV portion, so that's your UVA. If you look at your sunscreen bottles, it says blocks UVA, UVB. UVA is a longer wavelength, so it's going to be anywhere from like 315 to 400 nanometers. Okay, and it's going to pass completely through the ozone. It's not going to be absorbed, so it's going to contact you. And what that can have the potential to do is to take these pyrimidine bases, which are nucleotides, and we'll talk more about that when we focus on biochem. But pyrimidines are your C's and T's. And when those are adjacent to each other in a DNA sequence, it will cause them to dimerize or bind together. And so what's going to happen is when now you go to replicate that DNA, the polymerase that's chugging along and transcribing the complementary strand is going to get confused when it gets to that dimer. It's not going to know what to do, so it's just going to pop in some random nucleotide. And by doing that, it incorporates a mutation, right? So then after that, you start getting into these shorter wavelengths, and so that's your UVB, and that's going to be mostly absorbed by ozone, but some of it is still going to get through, and so will expose you to UVB. And then there's the ultraviolet C, which is ionizing radiation. Now, luckily for us, most of this is basically absorbed by ozone, so it doesn't come down to attack us. Now, this is what we use in tissue culture hoods and stuff for sterilization. Okay, because this type of radiation, this ionizing radiation, is going to basically just break the double strands of DNA in half. So double-stranded breaks, meaning it breaks not just one strand, but it breaks it all the way through. And so that can be repaired, but usually it leads to mutations or just death. Okay. And so this kind of UV, this at this end of the spectrum, is again what's used to sterilize surfaces that may be contaminated with bacteria or viruses, because it breaks apart the germ's nucleic acid. And you might think about it. We've had discussions at LTCC if what would be the efficacy of getting some UV wands and rubbing them around the campus to sterilize, and really it all depends on, and what we'll get to later, exposure to radiation depends on distance and time. So the longer you're standing next to something that's giving off radiation, and the closer you are in proximity to that radioactive material, the greater your exposure is going to be. So having these wands isn't really that practical, because you don't just wave it past something. You got to kind of hold it up to that surface for 5 to 15 minutes at least. Okay. Now, interestingly, if you look at the non-ionizing radiation, you can see what this breaks down into. So once we get past the visible light, we get past infrared, we get into things like I said, like microwave radiation, AM, FM radio radiation, and stuff in power lines. Okay. And the further you get out, the less and less harmful it becomes. So the longer that wavelength. Also, the longer the wavelength, the more penetrance it has, which is why radio waves can go through walls and stuff, but microwaves can't, right? A microwave oven is contained. And interestingly, a big concern that's been popping up is the introduction of 5G technology, right? I know that people are even linking this absurdly to the outbreak of SARS-CoV-2, you know, and there's a lot of uproar, even in our community here in South Lake Tahoe, people afraid of the incorporation of 5G technology. The I won't. This is I'm talking about the effects of radiation, so I won't go into it a whole lot. But 5G is essentially um, a higher frequency for the most part that allows us to transfer information more quickly. Okay. And it incorporates a frequency range that's the same as the 2G, the 3G, the 4G. But then it also employs a second frequency range that's a little bit higher. Okay. And that's what people are freaking out about, I guess. But if you look at it, here's the range of non-ionizing radiation, and here's ionizing radiation to the right, and it's giving you examples of what to expect, how much radiation, or not how much radiation, but the frequency of the radiation from everyday household items like computers and radios and your cell phone. And then all the way up to things like tanning beds and X-rays and gamma rays, right? Now, if you look at a remote control for your television, it's 5.8 gigahertz. And that's about what 4G, 3G, and partly 5G, that's the range of this that we're talking about. The same range as a remote control. Okay, so if you're going to freak out about 5G, you might as well throw out your remote controls as well. But again, 5G is not just that frequency range of less than 6 gigahertz. It also employs a second frequency, which is what gives it its more peppy, speedy properties. That's anywhere, it says 30 gigahertz on here, but it's anywhere from like 24 to 52 gigahertz. Okay. But still well within the range of things that we're exposed to on an everyday basis. And even if we weren't exposed to some of these things regularly, this all is on the non-ionizing spectrum, right? And remember, non-ionizing radiation, you have to be subjected to it for a prolonged period of time, and really at a much higher gigahertz frequency for it to really show, at least scientifically, any adverse effects. So that's my 2 cents on 5G. That's where I stand. I'm not afraid of it. I say bring it on. What is the role of ionizing radiation, though, to our body? And because that's the stuff that really messes with us. So it can be a direct impact, or it can damage our bodies indirectly. A direct effect would be some kind of radiation source. Let's say it's UVB, or so UV that's kind of approaching that ionizing area on the spectrum, and it zaps your DNA in your cell and causes a double strand break, or it ionizes the molecules in that DNA, causing free radicals. Well, what's going to happen? Well, if it's UV, you're going to get a sunburn, right? And your skin is going to turn red, and it's going to turn red, and it's going to feel hot to the touch because all the blood in your body is rushing out to the surface to bring out the inflammation response in order to take care of these irradiated cells. And when I say take care, I mean get rid of them, so that they don't become cancer cells, right? Because what happens, how does cancer happen? Cancer happens when cells don't know when to stop dividing. And they don't know when to stop dividing when their cell cycle checkpoints have been mutated. And they get mutated when they're irradiated, right? Or, in some cases, when they're irradiated. That's why exposure to the sun causes, in some cases, skin cancer. And why it's so bad to get sunburns when you're a kid versus older. It's never good to get a bad sunburn, but when you're a kid, your immune system is still, it's robust, but it's still kind of in its infancy, so to speak, and so it's not as good as at detecting these cancerous cells sometimes. Now, your skin also, so that redness is the blood rushing to the surface, and then after a while your skin will peel, right? When your skin is peeling because the skin cells that have been irradiated and have DNA damage are undergoing a process called apoptosis, or programmed cell death. It's the way for the cell to say, okay, I've been compromised, I need to kill myself. And so it does. And as a result, hopefully you're protected, right? But if you're not, then if one cell doesn't undergo apoptosis, or it evades the inflammation response, then that's going to survive and it's going to turn into a tumor. Okay. Now, what's an indirect effect? Well, this ionizing radiation can come into contact with the water in your body. And when it does, it can ionize that water. It can kick off an electron and form an ionized water molecule, H2O plus. And this ionized water molecule will then interact with a nearby water molecule, a normal water molecule, and it will form, as a result, H3O plus, or hydronium ions. And as a result of that happening, it's going to then leave this byproduct of this hydroxide radical. And a hydroxide radical it's a free radical. And so what it's going to do is it's going to go and then attack certain molecules in your body. And as we'll talk about when we get into organic chemistry, hydroxide groups greatly change the molecule. So if you put an OH functional group onto an organic molecule, it's going to change the behavior of that molecule. It becomes a different molecule, right? And so if this free radical now attacks something that's not supposed to have that hydroxide group, then it's going to change the function of that molecule. It's going to render it functionless, perhaps. And so that would be the indirect effect. The radiation harming the water molecules and then causing free radicals to then attack your biological molecules. And so that's why doctors and scientists recommend eating foods that are rich in antioxidants, right? So coffee and acai berries and blueberries, these things have antioxidants, which are like sponges for free radicals. So they provide a substrate, if you will, for the hydroxyl group or other free radicals, they're not always hydroxides, to bind to, so that they don't attack your body. Now, not all radiation is bad. Well, actually, this is bad. I'm getting ahead of myself. What is something that's common in South Lake Tahoe, particularly? Exposure to radon gas. Okay, radon 222 emits alpha particles, which we talked about last time. It has a half-life of 3.82 days, And it's in this decay series, which we'll talk about next time. A decay series is just the stepwise process that a radioactive isotope will go through to reach a stable form. Okay, so if we start with uranium-238 and it starts undergoing radioactive decay, it's not necessarily going to be stable after that first decay event. All right, so it will just keep on breaking down until it does reach something that's stable. But one of the things that uranium-238 breaks down into is radon-222, which is also radioactive, though. Okay, and uranium-238 happens to be present in things like rocks and dirt and granite. And what's vastly abundant in South Lake Tahoe? Granite. Okay, and because radon is so much more dense than the air, it's going to just kind of pool, um, like in your basement or in your crawl space. And if you have any cracks in your foundation, it can seep in from the soil and the granite where the uranium is actively breaking down. And if you happen to have your hot water heater or something in your basement, then it can infiltrate into your hot water heater and then contaminate your water. And so it's something that depending on who you talk to in Tahoe, is a really big deal, or not a very big deal, but it's something to consider. It's probably a good idea to have some kind of radon test, just so that you can rest assured that you're not being exposed too heavily to radon gas. Now, what I was going to say, not all radiation is a bad thing, because we can use it, of course, to treat cancer, which, again, ironically, you can get cancer from radiation, right? From a sunburn. And once you get cancer from radiation, sometimes what the oncologist will do is they will irradiate the tumor using a different type of irradiation, they use, what is it? It's an X-ray. It's like called a soft X-ray or something like that. But so it's kind of funny that it's a circular event where you get the cancer, and from a similar source that you're using to get rid of the cancer. But anyway, in this case, we can use radiation in our smoke alarms at home. Okay, so most smoke alarms will have this radioactive source of americium-241, and that's going to emit these alpha particles into this chamber. And the alpha particles are going to then ionize the air inside this chamber. And with that ionized air present, now you can pass an electrical current from the negative to the positive end. Okay. But when you burn that thing you're cooking on the stove, or some kind of fire breaks out for whatever reason, irresponsible, reckless use of candles, I don't know, then the smoke particles will enter into that chamber and will block, to a certain extent, the flow of these ions that were created from the alpha particles of the americium-241. And when they block the flow of those ions, it dampens the current that's being produced. And once the current, that electrical current, is dampened, it triggers the alarm. So yeah, that's a case. That's a situation where radiation is being, wielded to our benefit. Right? So how do we measure radiation? There are three major ways. One is a Geiger counter. So um, what it does is it 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 if there's radiation in the vicinity, it's going to ionize the gas in this wand here. Okay, so you wave this thing around, and if there's ionization happening, you're going to get a click. So each click is going to represent um, a certain number of ionization events. Okay, and so the rate of ionization, so how fast it's occurring, is going to be proportional to the overall amount of radiation in that area. And I think the Geiger counter is what you used for the radioactivity lab that you did a couple weeks ago. So click, click, click. That's low amounts. Click, 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 click. Right. The more clicks, the more radiation is around. Oftentimes, Geiger counters are used in labs. I used to use a Geiger counter when I was working with P32. Um, so that's where you'll see them. You probably won't come across them unless you're working in a lab setting. Another type of way to measure radiation is a scintillation counter, where you have these little vials here, and you put this this kind of thickish, clear material called scintillator. Okay, and within that, you also put your sample that you want to measure. It's usually like a liquid sample, and um, that scintillator is going to give off light when it comes into contact with ionizing radiation. Okay, and so there's going to be a machine that's attached to those detectors detecting the light emission, and it's going to convert that into this electrical signal, which will then convert that into a readout to show you how much radiation is in that sample. Okay, and you can figure it out. You can translate it by the volume that you put in there. And this is another instrument that you'll find particularly in a lab setting. So I've used this before too. Um, but something that you may encounter not in a lab um, is the third type of measurement, and that is just a dosimeter. Okay, and these are just going to be mostly personal devices. They could be badges that you wear. It could be, in this case, in the picture, kind of like a monitor, and these are for um, people who work around sources of increasing radiation. So flight attendants and pilots, just by flying, are exposed to greater amounts of radiation, and so they have to wear these just to monitor their exposure. Pregnant women will often wear these if they are in jobs that have an increased chance of being exposed. Also, if you're being given radiation in 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 some kind of bead form. So I know that for prostate cancer, oftentimes they will irradiate the cancer by implanting these radioactive beads into the site near the prostate, to where the cancer is, to destroy the cancer cells. And so they'll give the patients these dosimeters so that they can monitor the release of that radiation, and just see what their overall exposure is. Okay. Now, again, measuring radiation on living tissue is complicated because our tissue isn't just a homogeneous sac, right? It's got skin and bone and muscle and ligaments and tendons and other internal organs that all are going to have a different degree of penetrance for radiation. And so we have to tailor how we measure the radiation depending on on several different parameters, okay, or variables. And we have this acronym READ, which stands for radioactivity, exposure, absorbed dose, and dose equivalent. Okay, these are the 4 variables that we take into consideration when we essentially try and figure out what somebody's interaction with radioactivity is. Okay. So for radioactivity itself, that's measuring the number of disintegrations per second. Right? So measuring how many radioactive decay events have occurred in a given unit of time, in this case, a second. The more disintegrations per second, the higher the exposure is going to be, right? And remember, it's a time and a distance game when you talk about exposure. The units are Curie or Becquerel. Becquerel is the SI unit. That's going to be 1 disintegration per second. So every second, there's only 1 radioactive decay occurring. Okay. The Curie or millicurie is much larger. A Curie is about a little over 1,000 disintegrations per second. Okay, so it's used in a more practical sense, like in medicine, where you're going to have where 1 disintegration per second isn't that big of a deal. You got to get into higher disintegrations per second before it really has a biological relevance. Exposure is the number of ions produced per volume. Okay, so the number of ions produced per volume. So it's not it's different, right? It's not disintegrations per second, it's ions per a given amount, not of time but of mass, right? And the unit we use for that is the Roentgen. Next, we have absorbed dose. And so this is going to be the measurement of radiation directly deposited into a given sample. Okay, so now we're really honing it in and getting more and more focused. We were just looking at kind of at the beginning with radioactivity, just what's happening with that radioactive material in a given time. Now we're really looking at how much radiation is going into some amount of matter, right? And the units we use for that are grays or rads for radiation absorbed dose. Okay, and a gray is going to be 1 joule of energy, because right, radiation is energy, right? Radiation is energy, and therefore we can quantify it using the unit of energy, which is joules. So gray is going to be 1 joule of energy per kilogram of tissue. That's the SI unit. Whereas a rad is going to be 0.01 grays or 0.01 joules of energy per kilogram of tissue. And remember, when we talked about the different types of radioactive particles and rays, we said that they had different levels of penetrance, right? So alpha particles can be stopped with just pretty much a sheet of paper, okay? Whereas beta particles depending on the graph you're looking at, can either go straight through your hand or can at the very least go through your skin into the meat, right? And then neutron definitely through your hand, through certain types of metal, but then we'll stop at water. And then finally gamma going straight through any kind of biological tissue, and it won't stop till there will pretty much will go through a lot of lead too, depending on the thickness. All right, so the effects of tissue and radiation, the effects of of radiation on tissue depends on the absorption, and the absorption depends on the type of radioactive particle that's being emitted. And that brings us finally to our dose equivalent. And this is when it really gets applicable and puts it into perspective on what it's doing to us biologically. Because the dose equivalent is the measure of tissue damage done. So it's looking directly at the damage. And it takes into effect the tissue type and the radiation type. So is it skin? Is it skin with alpha particles? Is it bone with beta? Is it bone with gamma? So on and so forth, okay? And the SI units for this are sieverts, but we also look at Roentgen equivalent for man, or REMS, okay? And that's what I was talking about. I think that was those were the units in that chart that I showed at the very beginning. REMS. So we've dialed it in completely, right? We've looked at just at the beginning radioactivity and just what's going on with that radioactive material kinetically, if you will, and got broken it down all the way to how much radiation is being delivered to a sample, right? A kilogram, how many joules are going into a kilogram, and then now taking into effect, well, what's the consequence of that? What kind of damage has been done? Was it altering the blood chemistry like we talked about, or making someone sick to their stomach, or is it more like, well, could this be something that's causing hemorrhaging? Okay. And this just kind of breaks down some of the more this is not a comprehensive thing of read. It's looking at activity of source. So that's this top one is radioactivity. The first one, so becquerels and curies, and gives you a brief description of what's going on, and then an absorbed dose. So the grays and the rads, and then biologically effective dose, or dose equivalent, sieverts or REMS. Okay, and so this is just kind of the breakdown, if you want to have that, to be able to differentiate these different ways of the different metrics of measuring radiation. All right, so let's go back to this again, and let's think about, now that we understand what REMS are, and keep in mind that 5 to 10 REMS are going to cause certain changes in our blood, okay? And that you have to get 5 to 10 times that before you really start, before you really notice the effects, okay? So in order to get nauseated from radiation, you need to have 50 REMS. And then I'm not going to go through all this again, but I just wanted to put this in perspective, because when you look at this graph, this is looking at the regulatory limits of radiation exposure, and it's looking at it in millirems, okay? So at this top bar here, annual nuclear worker dose limit. is 5,000 millirems, or 5 rems, right? So a nuclear worker is, the annual dose that they're supposed to have is at the very minimum threshold of the range that it can go to. Okay, so put that into perspective. If you work at a power plant, you shouldn't be having any of these effects here, right? This is the maximum. And then so you can compare and see how that compares to a whole body CT. So if you have a CT scan, that's already going to give you 1 rem, or 1,000 millirems. So 1/5 of the annual exposure that a nuclear power plant worker is allowed to have. Average US annual dose is only 602 millirems. So far below the the threshold of what would or should alter your blood chemically, right? And then you can look at these things like how many, just from your body is going to irradiate itself to a certain degree, because you are, again, every element has radioisotopes, right? And so you're going to be encountering those radioisotopes through daily life, and incorporate them into your body, and then break them down. And so, and then the cosmic rays that come from space mostly are filtered out through our atmosphere. But again, when you fly in a plane, like a transatlantic flight here, so going on I don't know, about an 8-hour flight, you're going to be in thinner air, right? You're going to be higher up. And so you're going to be exposed to more radiation than if you were keeping your feet planted firmly on the ground. And to keep in mind that the EPA has said that it's safe to drink water that would give you a dose of 4 millirems. Okay. Now here's a cool infographic. I'll go through this just for fun, and then wrap it up. I really like this because it kind of puts it into perspective. This is looking at microsieverts. Okay, so we've moved on from rem to sievert. So it's a little bit different, but not too bad. I think that what is the difference between rems and sieverts? I want to say I thought it was 1-to-1, but I could be wrong. No, 1 sievert is 100 rem. Okay, so 100 rem in 1 sievert. So sleeping next to someone is going to give you 0.05 microsieverts. And so that's going to be depicted by this 1 blue square. Okay. So you're going to get irradiated to a certain extent just by being in proximity to another person, because remember, our bodies are giving off radiation to a very limited extent. Now, if you live within 50 miles of a nuclear power plant for 1 year, you're going to double that. And you're going to have about 0.1 microsieverts, which is also the same as eating 1 banana, because bananas have potassium, and potassium has radioisotopes particularly potassium 40. And they actually, it's not a scientific form of measurement, but there is such thing called a banana equivalent dose. So kind of like an informal way of looking at radiation exposure by applying it to something pretty basic, like eating a banana. So it can put it into like kind of layman's perspective. And then if you live within 50 miles of a coal power plant for a year, you're going to get exposed to more radiation, 3 times the radiation, right? Than living that same time period, that same distance to a nuclear power plant. Go figure. And then we're looking at, if you get an X-ray because you broke your arm or you think you broke your arm, that's 1 microsievert. What's this? Extra dose from spending 1 day in an area with higher than average natural background radiation, such as the Colorado Plateau, 1.2 microsieverts. And again, this is all very, very low levels of exposure. Okay. Remember, if we look at, I guess, if we looked at the transatlantic flight, it was like 2.5 millirems, right? And so here we're looking at 40 microsieverts from flying to New York to LA. So all of this is well below anything that should alter you chemically. Okay, so whether it's a dental X-ray, or just your background dose received by the average person over 1 normal day. Okay, so just in a given day, by being alive, we're exposed to 10 microsieverts. But what happens when we increase this? So let's take all of this exposure. So every little blue square, we're going to add up all those microsieverts and say that that's the equivalent of whoops, jump the gun. That's the equivalent of 3 green squares. Okay. So let's put that into perspective. Extra dose to Tokyo in the weeks following the Fukushima accident. So that happened, man, when was that? Was that like 2011 or something? 2000, yeah, I want to say it was 2011 when it was a tsunami that hit Tokyo and leached a bunch of radioactivity into the ocean because they had a power plant right there on the coast. This is how much you'll get. So you'll get basically not all of this radiation combined, but almost all of it. Living in a stone, brick, or concrete building for a year, 70 microsieverts. Interesting, huh? And then, I'm not going to go through every single thing, but I'll post the slide deck, and of course you can look at this, and I just think it's pretty cool because it, like I said again, it really puts into perspective the difference between, say, getting a mammogram and eating a banana, right? Or a mammogram and flying, right? So a mammogram is probably going to be like 5 or 6 times all of this combined, right? All of the blue combined. But it's not going to be nearly as much as getting your head scanned, right? I've had a CT scan. And so that's like, what is that? That's over 4 times as much as getting a mammogram. And some people don't get mammograms because they're afraid of the exposure. And really, again, it's not that bad when you think about The maximum yearly dose permitted for US radiation workers is 5 millisieverts, or no, 50 millisieverts. And I mean, that is a lot more radiation than just one mammogram. Now, this is a yearly dose, whereas a mammogram or a CT is going to be just a one-off, shot. So it's much more concentrated, but still. Dose from spending an hour on the grounds at the Chernobyl plant in 2010. Well, it's 10 years later. It's 2020, and I don't know how long I've been lecturing, but I've been at Chernobyl for probably about an hour. So we'll see. I don't have my dosimeter on me, so I have no idea what kind of radiation I've encountered, but I think I'll be okay. So this right here, this big chunk of green, like I said, is the yearly dose permitted for US radiation workers. If we take that all of the green, right? Let's go back, all of this, and we say that it's the equivalent of now, oh, come on, draw, of this many, what is that, red? Now we're looking at things like what's a fatal dose, even with treatment? 8 sieverts, okay? Which that's a lot. I mean, that's a lot of these events all at once. So you got to get you have to have a lot of CTs, a lot of mammograms done all at once to really kill you. Right? So they're pretty benign. Usually fatal radiation poisoning, survival occasionally possible with prompt treatment. So if we have that from 8 to 4 sieverts, we still are probably going to die. Okay, chances are. If you want to just get a dose of symptoms like nausea and vomiting and diarrhea, then 400 millisieverts is what you want to go for. Okay. And if you want to get severe radiation poisoning, but mostly not fatal, then I would not go past 2 sieverts if I were you. If you take all of these red squares, which are a lot of green squares and are a lot of blue squares, and we're talking, you got to eat I don't even know how many tons of bananas, okay, to equal up what we're going to next. Okay, all of this is equivalent to 10 minutes next to the Chernobyl reactor core after explosion and meltdown. So I'm assuming that must have been in 1986 when that happened. So 50 sieverts. And then you can imagine, what happened to those poor people that were the workers of the nuclear power plant. They looked like they had sunburns, right? Their skin turned red because it's not, the sun it's not like you're getting, cooked per se. I mean, you are, but it doesn't have to be the sun that gives you that red effect. You'll look like you're sunburned from any kind of radiation because that is that concentrated, because again, it's damaging your DNA so quickly that it's causing this flush out of blood to the skin and to try and fix it. But if you have this exposure, there's no fixing it, right? You are gone, and you'll be gone quickly. So I think that was it. That's all I had to say. Is that it? Yeah, that's it. Let's stop sharing. I hope you enjoyed this. It was, chemistry light. Not really much that, there's no real material to assign for homework or to test you on. I just wanted to give you this lecture to give you a perspective on radiation and how it is applied practically, and how it affects us practically. Um, but there's nothing. Don't worry about this material being on the exam, or an ICA or anything like that. We won't we won't hold you accountable to knowing what the SI units are for these different things. But just hopefully you got something out of it, and you know, you can appreciate radiation. You can go get your radon test for your house to make sure that you're not getting exposed to radon 222. And that's it. We'll see you next time. I'm going to leave Chernobyl now because I don't know. I saw that infographic and it's now freaking me out. So bye.